Bismillahirrahmanirrahim. Dear students of mathematical techniques for boundary value problem, MS first and third semester. Today we will start our third online lecture. In our previous lecture we have introduced a new method called the method of straining coordinates for the solution of a singular perturbation problem concerning ordinary differential equation, and we saw that the presence of a secular term in the regular expansion solution causes the difficulty for us. Therefore, in order to remove that secular terms, we have introduced this method. In our coming few lectures, we will also focus on the different forms of that method, because this is an important method from engineering and physics point of view, where we have lot of singular perturbation problems concerning ordinary differential equations. So today we will briefly describe this method, which is known as the method of strained coordinates. This method is basically a technique for dealing with the certain types of non-uniformities which occur in asymptotic expansion. As you saw that the obtained solution by the regular expansion in our previous case of the differential equation was not uniformly valid for all t, and that was actually unbounded, and that was the source of non-uniformities. So with the help of ordinary asymptotic expansions, the solutions of such problem contains non-uniformities, and that solution is not valid for all t. Therefore, the presence of secular term will forces us to develop the new technique. We will develop a method for rendering the approximate solution to some of the differential equations. We will try to find the solution of some of the differential equations with the help of this technique. This technique goes back to the 19th century. This technique actually was developed by the Lindstedt, which was an astronomer in 1882, and he wanted to avoid the appearance of the secular terms in perturbation solution of the equation, such as a second order ordinary differential equation u double prime plus omega naught square u is equal to epsilon f of u prime, where epsilon is small. This is actually the governing equation for an oscillatory system, or you can say that an oscillator, whenever a motion is described by an oscillator, then such type of equations occur for that problem, and we can also call it as the Duffing type equations. And Lindstedt actually developed this method to avoid the secular term for this equation. What was the basic and fundamental idea in the Lindstedt method? It was based on the observation that the non-linearities alter the frequency of the system from their linear one omega naught to a function omega of a small parameter एप्सिलॉन. अब लिंस्टेड ने जो ये टेक्निक अप्लाई की, उसका जो बेसिक कंसेप्ट था, बेसिक आइडिया उसका था, उसने ये ऑब्जर्व किया कि जो हमारे पास फ्रीक्वेंसी है ओमेगा नॉट, it actually changes from its linear value omega naught to the function of the small parameter epsilon, which in turns take the value omega of epsilon. And this idea was because the important parameter in this problem was the frequency omega naught. Therefore, this idea was generalized to any method, that is, to account for this change in frequency, he introduced a new variable tau instead of time at t, and which has the relation tau is equal to omega into t. Actually, our independent variable was t, and the frequency omega depends on t. Therefore, we use this new variable, as you see in our previous example, that we change our independent variable t by expanding it in the power series of, or in the asymptotic expansion in the powers of epsilon. So this is the basic idea once again, that your independent as well as the dependent variable, therefore we can expand omega and u in powers of epsilon as. अब चूंकि हमारे पास frequency change हुई, that is the I am telling you the whole story of the this technique basically, कि इसके पीछे जो है क्या concept है. So therefore we can expand our dependent variable u in the powers of epsilon in the form of a new variable tau, not in the original variable independent variable t. So therefore u can be expanded in the form u naught of tau plus epsilon, u1 of tau plus epsilon square, u2 of tau, to so on. Similarly, omega is expanded in the powers of epsilon as omega naught plus epsilon omega 1 plus epsilon square omega 2 up to so on. Then he choose the parameters omega I, where I from 1 greater than or equal to 1, 1 से बड़ों के लिए omega 1 omega 2 up to so on, not for omega, to prevent the appearance of the secular terms. तो ये basically जो हमारे पास ये जिस दूसरे पैरामीटर पे भी आप expansion apply कर रहे हैं, which we have applied in our last section on time, then we can choose the values of these omega 1s in order to prevent the appearance of the secular terms. Secular terms से अगर हम बचना चाहते हैं तो हमें इन जो omega 1 omega 2 up to so on है, इनकी वैल्यू फाइंड करनी होगी. Poincare in 1892 proved that the expansions obtained by the Lindstedt techniques are asymptotic. Therefore, after his contribution, this method is termed as Lindstedt-Poincare technique. The Lindstedt method applies only to the periodic solution. More general method given in next few lectures can handle the transient solution as well. ये जो हमारे पास method है, that is applicable only to the periodic solutions. तो ये बात याद रखें कि जो हमारे पास solutions आएंगे, जो हमारे पास initial solutions cos sin या ऐसे फंक्शन जो पीरियोडिक हो, उन्हीं के लिए एप्लीकेबल हैं, बिकॉज द बेस्ट एग्जांपल ऑफ द पीरियोडिक फंक्शंस आर द ट्रिग्नोमेट्रिक फंक्शंस. सो दिस मेथड इज जनरली एप्लीकेबल टू द ट्रिग्नोमेट्रिक टू द पीरियोडिक सॉल्यूशंस, एंड we can handle the transient solution as well, जो time dependent हो. Transient solutions means which depend upon the time. But for the periodic solution, the Lindstedt method has a distinct advantage over the other methods, both in simplicity and accuracy. This method is specific to the periodic solution because ये एक simple है और इसके बहुत ज़्यादा advantage हैं over the other existence method. Therefore, in case of the periodic solutions, this method Lindstedt technique is very useful. And secondly, this is simple as well as the accurate. The regular expansions will continue to be referenced for purpose of comparison, but the remainder of this paper will focus on the techniques developed specifically to improve the shortcomings of the regular methods. हम comparison के लिए regular expansions को भी देखेंगे, but the main focus of this topic in coming few lecture will be the Lindstedt techniques, which can prevent or which can improve the secular term from our problem, and we can obtain the solution. So basically, if I will recall this whole method, Lindstedt Poincare technique for the solution of singular perturbation problems concerning ordinary differential equation, is that we have to expand both the dependent as well as the independent variable in the powers of एप्सिलॉन, स्मॉल पैरामीटर एप्सिलॉन. कि हम क्या करेंगे कि उस सेकुलर टर्म्स को से अवॉइड करने के लिए हम जो हमारे पास इंडिपेंडेंट वेरिएबल होगा और जो डिपेंडेंट वेरिएबल होगा, दोनों को हम एक्सपैंड करेंगे, और फिर जो हमारे पास इंडिपेंडेंट वेरिएबल्स में जो हमारे पास उसकी एक्सपेंशन में जो हमारे पास कोफिशिएंट होंगे, लाइक ओमेगा 1, ओमेगा 2 अप टू सो ऑन, because you will see in our next examples this first coefficient is usually taken as the 1. इसको हम usually क्या करेंगे, 1 लेंगे. आपने लास्ट एग्जांपल में देखा भी था कि हमने टाइम के लिए जब इसको, ये एक्चुअली ओमेगा, मैं आपको पहले बताया कि दिस वाज द डिस्क्रिप्शन ऑफ द मेथड. बेसिकली अवर इंडिपेंडेंट वेरिएबल मोस्टली विल बी द टाइम, सो वी हैव टू एक्सपेंड टाइम, जैसा कि आपने पहले एग्जांपल में भी देखा था. So the first coefficient we will take will be 1, और जो बाकी ये W1 और W2 आएंगे, ओमेगा 1, ओमेगा 2, इनकी वैल्यू हम जब कंप्यूट करेंगे और यहाँ पे सब्स्टिट्यूट करेंगे तो दे विल गिव अस द टर्म्स फ्री ऑफ द solution, free of the secular term. So this is the whole story of this method, and in our coming few examples we will in detail study how we can solve the problem with the help of this technique. Thank you.